chapter 8 here, and we had just started talking about oxidation states. Now, do you all remember finding oxidation states before? Okay, so I gave you some basic rules. We know common charges of certain elements, and so basically when in doubt, those common charges are going to be what they are. Especially for the halogens and the and oxygen, the alkalis, and the alkaline. Those tend to be what we would think they would be. So what we're going to do is we're going to take a look at how we can figure out what other elements would be based on what we have. So if we have, well, first of all, if we just look at something simple like H2O, the rules say that the oxidation numbers have to add up to 0 because this is a neutral compound. What would we expect oxygen to be? -2. What would we expect hydrogen to be? +1. And that's for each of those hydrogens. So we would say 2 times +1 plus -2, and lo and behold, that equals 0. Okay. So now let's do something where it's not necessarily obvious. So nitrogen can kind of change its oxidation state. And we have, let's say, sodium nitride. So sodium is one of those that if it's in a compound, it's always going to be the same thing. So what is this one going to be? +1, right? So we have 3 times +1 plus whatever n is going to be equal to 0. So 3 plus n equals 0. So n equals what? -3. And that makes sense for the column that it's in. All right, let's do an ion. So now we've got nitrogen again. But it can't be -3 because if it were -3 and oxygen were -2, then we'd have a really big negative number. So this is showing us that nitrogen is going to change its oxidation state. So oxygen, it's more electronegative, so it's going to be the number we'd expect. So we have nitrogen plus 3 times -2. Is this going to be equal to 0? No, this is going to be equal to the charge of the polyatomic ion. So since that's a -1, that will be equal to -1. Okay. So then nitrogen -6 is equal to negative, is that right? -6 is equal to -1. 5. So we're going to add we're going to add +6 to both sides. So 6 minus 1 is going to give us 5. That's the range that nitrogen can go. It can go as high as +5 and as low as -3. And for our P block elements, particularly the nonmetals, their range tends to be 8. The highest it can go is 8 more than the lowest it can go. Oxygen can go +1, but really likes to be 0 or negative because it's more electronegative. But if we look below that, sulfur in that same column, of course, it can be -2, but it can go as high as +6. So if I have SO3, or even if we did selenium oxide instead of sulfur oxide, same column, still works out the same. We would have selenium plus 3 times -2 is equal to, that's a neutral compound, so that's 0. So selenium is equal to +6. So that column can go between +6 and -2. So what do you think the highest that, say, iodine could be? Nitrogen's highest was +5. Selenium's highest was +6. Next column over, what should it be? +7. So usually the halogens are going to be -1. The only time they're not -1 is when you mix them with each other or with oxygen. And so we call those interhalogens when they're mixed with each other. Whichever one is closest to fluorine is the most electronegative. And so that's the one that gets to be -1. and the other one we figure out by solving. So let's take these two, BrCl3 and IF7. So chlorine here will be -1. Fluorine is always -1 in compounds. See if you can figure out what bromine and iodine are going to be. All right, so what do we decide that bromine was? +3. And iodine? -7? +7. So what about KMnO4? Now we've got 3 elements. And generally, if you recognize an ion, you can kind of separate the ions and do them separately. It works out the same way, but we can do it this way too. So potassium's in group 1. That's +1. Oxygen, we said, would be -2. So we have 1 plus manganese plus 4 times -2 is equal to 0. So this is -8 and 1. Manganese -7 equals 0. What's manganese? +7. And so later on, we're going to look at some periodic trends. And one of those trends allows us to see that that column with manganese behaves a lot like the halogens, which is kind of weird because halogens are nonmetals. And the column with chromium behaves a lot like the chalcogens, the oxygen column. And so this formula is very similar to this formula per chlorate. This is per manganate. This oxidation state is also +7. Just like there's a sulfate ion, there is a chromate ion. They both have the same oxidation state. Okay, so I'm going to hand you this sheet, and I want to look at figure 8.2. This is just showing us the observed oxidation states for some of the first main group elements. Remember, main group is not including the transition metals. So we've got the S block and the P block. And so you can see there's kind of a pattern there. As we go across, we increase our lowest possible oxidation number by 1. And then instead of including all of the oxidation numbers, when we have multiple oxidation numbers that are commonly seen, what tends to happen? We don't have every single oxidation number between +5 and -3 for nitrogen. Which ones do we see most often for nitrogen? Well, if we look at nitrogen on the bottom here and then follow up, we can see the -3, and then up at the top, we see the +5, but not +4, we see +3, right? Okay, similarly, if we look at sulfur, we have a -2, and we don't see things like -1. We don't see things like +3. We only see the even numbers. So the common oxidation states tend to be separated by 2. So that's a pattern that is observed. Part of that is because one of the things that commonly does the oxidizing is oxygen, and oxygen requires 2 electrons in order to go from its 0 to its favored state. So you have that. So if you look at any element that has things both at the bottom and the top, you should see that they are separated by 8 or less. And so that basically goes to either taking on enough to fill the octet or giving up all of the valence electrons. So nitrogen has 5 valence electrons. It would need 3 more to fill its octet, so that would be -3. Or since it has 5, it can take away 5 and become a +5. Okay? So let's think about other kinds of numbers. So when we do dot structures, one of the things that we can do is find the formal charge, because we know that there are different ways the electrons can arrange themselves. And based on how they arrange themselves, we want to have the formal charge closest to what? 0. So that's favored for a good structures, to have the formal charge equal to 0. So when we assign a formal charge, that's going to be equal to our valence electrons. The ones that carbon already started with were 4. The ones that oxygen already started with were 4. Plus the lone pair electrons, plus half the bonding electrons. Or sometimes I say all the dots plus the lines, because a line is 2 electrons if we take half. Okay, so if we think about what that means, if I draw this with dots, what we're saying is this oxygen gets to count all of the lone pairs and half of those bonding electrons. And so we're saying these electrons that are between here are shared equally between the 2 atoms. So what kind of bonds share electrons? Covalent electrons. So formal charge treats all bonds, right? Everything is equally shared. Now, in reality, are the electrons between oxygen and carbon equally shared? No, because oxygen is more electronegative. So the reality is this, if we were to look at where the electric charges were, the oxygens, the outsides would be a little bit more negative and the carbon would be a little bit more positive. But formal charge treats them all as this is 0, this is 0, this is 0. Because if I plug in their numbers into the equation, I get 0. Oxidation number says the more electronegative atom keeps all of the electrons. So if I were to assign an oxidation number, I could think of this, if I were trying to think of it like a formula like we do for formal charge, I might say, well, the valence electrons minus all of the electrons that are lone pairs. And if I'm the more electronegative one, all the electrons in the bond. So we would say, okay, for oxygen, that would be 6. Its valence number is 6. And then there's 8 assigned electrons, so this would be -2. Carbon has 4 valence electrons, but it doesn't have any dots in its circle. So it is going to be +4. Okay. Now, is this an accurate picture here? Not really. We do have a negative charge on the oxygens, but we know that nonmetals share electrons. There is some sharing going on. So the truth is in between. Oxidation numbers work really well for ionic compounds because ionic compounds don't share quite as equally. When we think about oxidation numbers in our freshman year, I say, well, for the metals, just think of it as the charge. The true charge on something that is 3+ would actually be less than 3+. It'd be like 2.5+. But we always use the oxidation number, the 3+. That oxidation number doesn't truly represent what's going on in a covalent compound, but it does help us to understand if this is going from a +4 to something different, that there is going to be some change in energy because the electrons are moving. And anytime we move electrons, we've got some energy going on. So let's say I do some reaction with this carbon, and I manage to get it to go to be methane. That would be an incredibly endothermic reaction. Hard to do, but let's say it happened. What would be the oxidation number on the hydrogens? +1, so with nonmetals, and that's usually where we see hydrogen, it will be +1. So if each of these is +1, what's the carbon? -4. So when we have something changing oxidation states by a large amount like that, there's 8 numbers difference, that's going to be a huge energy difference. So if we did the reverse and turned this into this, burning methane, does that produce energy? Yeah, you get fire, right? You're going to get a lot of energy out of that. Okay, and in fact, for carbon, that is the most energy that you can get out of burning a single carbon is when it's in the form of methane. If it's in ethane or propane or kerosene or coal, per carbon, you get less energy. Okay, what do I want to do next?